So we were discussing biasing the transistor with a constant current source, and we came up with the structure. And how did we come up? We came up with this structure because we were trying to ensure that a transistor has some. I have a current source I0 and I have this transistor M1. We wanted to ensure that the transistor M1 gets the current, the drain to source current of the transistor becomes exactly equal to that of a current source. And the motivation for that was to ensure that the GM of the transistor does not change. Right. So that was the whole motivation. The GM, we don't want the GM to change with respect to threshold voltage. So that was the reason we would have liked to do this. And then we noticed that if I simply connect the transistor, if we simply connect the current source to the drain of the transistor, this will not suffice because the current through a transistor is not the cause, it's the effect of something else, right? It's the effect of the gate to source voltage that is applied between the gate and the source terminals of the transistor, which meant that we needed, say, framework to generate that gate to source voltage automatically, right? So, for example, if let's say I know that a gate to source voltage fixes the current, and one might come up and say that I do my calculations and see that I0, let's say, equal to half mu n Cox W by L VGS minus threshold voltage whole square. This is the current equation approximately. And let's say I want this I0 to be 1 milli. I have a current source of 1 milliamps. So I know mu n Cox, right? I know W by L. All I need to do is to find out the appropriate gate to source voltage, and I take a voltage source and connect it like this. Okay, so I can do that in principle. If I'm in the lab, I can do this. Now, what are fixed? These guys are fixed. Threshold voltage is fixed. So if I can only apply this battery to be exactly equal to this VGS, then this right-hand side and the left-hand side equations are balanced, right? So then there should not be a problem. Then the transistor M1 would be perfectly sinking in the current of 1 milliamp, right? So as far as the mathematical balancing of equations is concerned, this is fine. But do you think in a practical scenario this is going to work? Given that, let's say, temperatures might change. If temperatures change, let's say threshold voltage changes, then will this way of connecting a voltage source and a current source simultaneously work? By work, I mean, will the transistor remain in saturation? Obviously, something will work, but will the transistor be appropriately biased? So let me repeat the question. The question is, I go to the lab and I hook up my circuit like the one that I have showed in the right-hand side. Okay. And how did I come up with those values? I came up with these values because I know the current equation, right? And I know that I need to sink in current of 1 milliamp. And let's say I know mu n Cox W by L, this guy is equal to, half mu n Cox W by L is 1 milliamp per volt squared. And I kind of know threshold voltage is 1 volt. So I set the battery voltage to 2 volt. And this equation is telling me that if VGS is 2 volt, the current through the transistor has to be 1 milliamp. And I have this 1 milliamp current source. I hook it up like this, right? So in a practical scenario, do you think this is going to work? By work, I mean, will the transistor remain in saturation? So VBAT is not varying, 1 milliamp is not varying, that I is not varying. But let's say temperature varies and let's say threshold voltage changes. So yeah, so that's always true, may or may not. So okay, so let's take an example, right? So I assume threshold voltage to be 1 volt. Let's say the threshold voltage changed to 0.9 volt, right? So now what's going to happen? Since battery is fixed, current source is fixed, those three I cannot change. Let's say UNC of W by L is fixed, and threshold voltage changed from 1 to 0.9. So what's going to happen? Which current decreases? So this current. So let's intuitively understand the transient behavior, right? So let's assume there is a capacitor here. Parasitic capacitance is always present, right? So let's say threshold voltage was at 1 volt. This was perfectly balanced. This current was also 1 milliamp, and no current was going into the capacitor under steady state condition. Okay, the capacitor was holding some voltage corresponding to the drain voltage. I don't know what that voltage is, but let's assume the transistor was in saturation. So now threshold voltage went from 1 volt to 0.9 millivolt. So now walk me through what is your understanding. What's going to happen? What's going to change? Instantaneously, what's going to change? Okay, so now before we go to current going to capacitor, can you comment on M1? Is M1 getting stronger or weaker? Weaker. Why do you say M1 is getting weaker? Yeah, M1 is trying to pull out more current. M1 is getting stronger, right? So this 1 milliamp current that M1 is trying to pull out, so will it increase or decrease? Up or down? Up. Okay. So this will increase. This will increase to plus some delta I, right? So can you approximate that delta I using small signal approximations? Can you approximate the delta I? So by the way, why do you think the current will increase? Threshold voltage decrease. So threshold voltage decreased by 100 millivolt. If threshold voltage decreases by 100 millivolt, approximately how much will the current increase? Why 0.01? Huh? It will be quadratic. So you will expand this term. Why will current reduce? Threshold voltage has decreased, right? So current will increase. See, other way of looking at it is that I can say VTH plus delta VTH, right? So threshold voltage has changed. So this is VTH plus delta VTH, correct? And then I expand that term. Right, it will increase. Now, how much it will increase depends on how you expand this, right? So when you expand this, you will have some delta VTH squared term, right? This is 0.1 millivolt squared term, and there will be one term which is linear, right? That delta VTH times this guy times 2, right? So what is that term? 2 times this guy in what is that term? The increase will be 0.2. I'm not concerned about the total increase. I'm just trying to lead you to something here. So what is this? So if I have this as, let's say, if I say this is VGS minus VTH plus delta VTH whole square. So this guy can be expanded as VGS minus VTH whole squared plus delta VTH whole square plus twice VGS minus VTH times delta VTH. Correct? And hold these guys multiplied by half mu n C ox W by L. So this guy gives you the quiescent, right? This guy is a second order term. What will this multiplied by this give you? That is GM. right? So how much, if I neglect the delta VTH squared, so essentially the increase in current is 1 milliamp plus GM times delta VTH, right? Okay, fine. So the moot point is you are dragging out more current, trying to drag out more current from M1, and that amount that you are trying to drag out is proportional to the GM of the transistor. Now, the guy from the top, the current source is giving you 1 milliamp. You are dragging out more than 1 milliamp. So what's going to happen? From where is this GM times delta VT extra current come from? From the capacitor, right? From this extra current will come from the capacitor, and obviously it gets connected to the ground. So that's how the incremental current will circulate between this capacitor, between the ground and the capacitor. But now what's going to happen here? This guy, this voltage, the drain voltage is going to increase or decrease. You are drawing current out of the capacitor node, right? So this current is increasing. You are drawing current out, right? So the voltage will decrease, right? So this voltage will decrease. So once this voltage will decrease, and when will this stabilize? When will this guy stabilize? If I neglect channel and modulation, when do you think will this keep on happening? Will this keep on drawing current out of the capacitor and the voltage will keep on decreasing? So essentially, if this guy is decreasing, so this voltage here, whatever it was, it will ramp down, because GM times delta VTH is constant. You are drawing out a constant current from a capacitor plate, which means you are drawing charges out of a capacitor at a constant rate, which means that voltage will linearly decrease. It will ramp down. So will it keep on ramping down forever to minus infinity, or it will stop somewhere? It will stop. Where will it stop? Or rather, when will it stop? Yes. Right. So it will stop when the transistor ceases to be in saturation. It's no longer in saturation, right? When the transistor no longer is in saturation, then obviously the GM drops, right? And the GM drops, and then you are going to get a GDS, right? So GDS will suddenly appear. And if you neglect channel and modulation in saturation, GDS is not there. But in linear region, GDS is obviously there. So now the extra current will flow into the GDS, and you will get some voltage, right? Get some steady voltage, right? So this guy will go and steady somewhere, and there wherever it will get steadied will be the case in which the transistor is a linear region. So the moot point that I'm trying to make here is that even though this mathematical equation is telling you that one current source and one battery will help you in biasing the transistor in saturation region, given that you do your calculations right, but in reality it will not, because you might be able to do the calculations right for one particular temperature, one very sweet point, but moment temperature changes, one of these parameters will change, and this equation will not be valid anymore, because you are not changing the battery voltage, you are not changing the current source for all temperatures, they are constant, right? Which means if you bias your transistor like this, you are setting it up for disaster. It's not going to work, right? So other way of thinking, the other way of philosophically thinking this, thinking about this is to think in this way. There is always a cause and effect relationship, right? There is one cause and one effect, which in mathematical term, when we say cause and effect, we essentially say what is a dependent variable and what is an independent variable. The dependent variable is the cause, and independent variable is the cause, and the dependent variable is the effect. In a circuit, the independent variable is the VGS, and dependent variable is the current. But if I have to fix the current, we are trying to make the current the independent variable, right? So which means that I have to make VGS the dependent variable on the current. You cannot have two different independent variables trying to set the same output. That's the main problem, right? Here the main problem is this is independent and this is independent of each other. And both of them are trying to impose one particular condition. And that condition can be imposed under one particular sweet point, right? So that's not possible, which means I have to make either one of them dependent on each other. If I make one of them dependent on each other, then it's not a problem. So the common source amplifier that we started off with, in that case, we presume that the battery is the independent variable and the current is dependent, right? So we were not fixing this current. Earlier, in the earlier part of the course, we were fixing the battery voltage. That was a dependent variable. Current was independent. There was no conflict. Now we are trying to say that I want the current to be the independent variable. If I say the current is the independent variable, then obviously I cannot make the battery, the VGS, to be another independent variable, right? Then there will be a conflict, right? So essentially, two current sources will be fighting each other. This battery is trying to fix a current here, and this current is trying to force another current into the MOSFET, and there is a conflict. They are fighting each other, and only way that can be resolved is letting the transistor go out of saturation. So that's not something that we want, which means that naturally the obvious lead is to say that if current is the dependent variable, I have to make the voltage the current is the independent variable, I have to make the voltage the dependent variable. So how do I do that? I do that by using negative feedback, and the argument of negative feedback we made in the last class, and that is by connecting the drain and the source, okay, drain and the gate, right? So in this case, naturally, if the threshold voltage increases, right? If the threshold voltage increases, then the gate to source voltage will also increase, thereby essentially changing this feedback, right? So you are asking the transistor itself to generate its own required voltage to sink in a current of I, right? That's all. That's the crux of the story. Okay. Any questions? Yes.
So how we reach to the point that MOS will stop going current from the
okay. So now, so why was MOS drawing current? Essentially, the capacitor. So the incremental situation was this then, right? Incremental situation was this, correct? So in this case, obviously, this voltage will keep on changing, right? Because you are continuously drawing current out of the capacitor plate, right? So once it goes into linear, this transforms into some other GM, this is GM lin times delta VTH, but you have a resistor here, and you have this here. So in this case, obviously, there is a solution because the incremental current can now circulate between the resistance and the current source and leave the capacitor as is, right? So this guy will not continuously decrease, right? Not convinced? So okay, so forget about this circuit. So if I tell you this is the current source and this is the capacitor, and this is the constant current source. So what will this voltage look like? It will keep on increasing. Now I put a resistor here. At steady state, what will that voltage look like? Anybody can answer. At steady state. Yeah, at steady state, the capacitor is no longer in the picture. All the current will flow into the resistor and voltage will settle to whatever it is supposed to. Right? So the linear region, it settles to linear region because this resistance appears. Right? Okay. So now that we know how to, at least we have one way of biasing the transistor using current source, and without using explicit voltage source. So we would like to use this configuration to make a common source amplifier. So again, a common source amplifier In a common source amplifier, obviously we have this structure. Let's say I call this M1. So in this case, we will have to connect an input, but first, before connecting an input, we need to bias the VGS of M1, right? So the biasing part we used to do by doing battery or doing this, right? So we have all sorts of ways of biasing. So let's say we were using a battery of VBAT, which was supposed to be equal to, if I wanted a current of I0, this VBAT was supposed to be equal to, I write out that equation and whatever I get, right? So that is equivalent to VTH plus under root 2 I0 by mu n Cox W over L. This equation you can get by expanding or expressing VGS in terms of I0, right? So because ultimately we are saying that I0 is, we want the VGS to be made automatically, right? So essentially we are saying that I0 is the independent variable and VGS is the dependent variable. So it is better to keep the independent variables to the left and dependent variables to the right. So that's how we write out these equations. This is fine, but now we said that we don't want to do this. We don't want to use this V battery. So what is the alternative? So again, the question is, this configuration, the GM of M1 is going to change, right? The GM of M1 is going to change if temperature changes, right? Do you agree? So if GM of M1 is going to change if the temperature changes, then the fix was using a constant current source bias, right? So for a constant current source bias, if let's say if I am able to make a constant current source bias, then this VGS is supposed to change if threshold voltage changes, correct? But in this case, it is not. So what is the fix? Let's say I have another identical transistor M2 for which the VGS of M2 does the VGS of M2 change with threshold voltage or it's fixed with threshold voltage? It changes, right? So looks like the VGS of M2 has all the good things that we want, but VBAT doesn't have. So what is the solution? Make what a function of GM? Right, exactly, right. So the VBAT is a function of GM in case of M2, but not in case of M1. So I want VBAT to be a function of GM, just like M2. So what is the solution? You can connect things. What do you do? Right. So I can simply steal the voltage from here, right? So I can, that voltage got generated in M2. If M1 and M2 are identical, if they have same W by L, and that is something that is we can kind of take for granted in an integrated circuit, because in a wafer you are making transistors which are very close to each other. So the properties of one transistor kind of is similar to almost similar to the properties of a neighboring transistor, as long as they are very close by, which is a fair assumption in an IC. Right? Not in a discrete component, right? If you are doing it on a breadboard, then this assumption is not always true. But in an IC, it's true. So if this is true, then I can essentially say that a replica of this M1 is M2, right? A copy of M1 is M2. I will generate the voltage in M2 and connect it here, right? So this seems to be fine, right? Do you agree? I mean, do you have any concern that this will work, not work? Okay, fine. So which means M1 now has all the good things so VGS of M1 is like now a function of threshold voltage, which is good. But now we have this now we have a source to connect, an incremental source. So earlier, how were we connecting the incremental source? So we have the battery here now, right? This battery is VGS. So I have to connect this VI-RS combination for a common source amplifier. What should I do? So I can connect it like this. So can I connect like this? Okay, what's the problem if I connect like this? Yeah, VI is VI is 0 with DC. VI is a sinusoid. So it doesn't have any DC. No, VI is, let's say VI is equal to VP sin omega t. Okay. So now tell me whether this is, so let's talk about quiescent. Right. Some of the I naught will flow into this guy, right? So under quiescent condition, this is shorted. So some of the I naught will flow this way. It will not, some of the I naught will not flow into M2. Right. So this is loading essentially, right? The stuff that you have added is loading your bias point. Right. So when it loads, what it will do? Capacitor, right? You have infinite capacitor. You put a infinite capacitor here. Let's say I call it CB. So we put a blocking capacitor here, which blocks the quiescent current from flowing out. So quiescent is fine, but what about AC? Right. So ultimately, we would want, our goal is to ensure that this guy is almost equal to VI, right? This is the goal. Right. That's what we did earlier also. So if I have to ensure this, what do I need to check? What do I need to check?
So there will be an AC current back to the left M2.
Right. So essentially, there can be a current. So this guy can load. M2 can load that node. Right. So which means I need to understand what is the amount of loading. Right. By amount of loading, I mean you need to understand what is the resistance. So what is the resistance looking into the gate, looking into this node? So I need to find out what is the incremental resistance looking in here. So how do I find out? I basically put the incremental model of this diode connected transistor, right? So incremental model of the diode connected transistor, you can, I mean, now I'm sure you're pretty adept at doing these. So I'm not putting the incremental model, I'm assuming I'm doing incremental analysis. So if I put a test voltage here, and I'm trying to figure out how much current it will draw. So this test voltage appears across the PGS, which means this current will be GM times V test, which means this current is I test is GM times V test, which means this Rn is 1 over GM. Correct? So now if that is 1 over GM, which means this guy, whatever I am seeing here, this resistance is 1 over GM. Okay. So if that is 1 over GM, what is the what do I need to ensure to what is it that I'm looking for to figure out whether whether loading is significant or not at the gate of M1? Right. So if I assume CB to be infinitely large, the only way VG will be approximately equal to VI if 1 over GM is much greater than Rs. Right. Ideally, 1 over GM should be infinite. Then VG will be equal to VI. Else, there will be some drop. Right. So now you see that RS is typically not in your control. Right. 1 over GM is also kind of not in your control because you want certain GM in this guy, and that's how you have set it. Right. So this as a designer, you cannot either you cannot control RS, and to some extent you even cannot control 1 over GM for loading purposes, because 1 over GM is being used to get the gain, right? So that's a problem then, right? There. So what is the fix? Which path? M2 to VG, meaning here?
Before CD.
Here? Here? Then the DC is gone, right? So you cannot do this.
So instead of a single capacitor, can we put an RC?
You can put whatever you want. Yeah, put whatever you want. Put what do you want to put it?
So, instead of one single, keeping only one single capacitor from M2 to gate of M1, I'm saying that we can put an R and C parallelly.
Where would you want to put R and C parallelly?
So the same place where you have just now drawn capacitor.
So you mean, so you want to put a parallel RC here between these two?
Parallel RC.
Okay, so this and this. Okay, firstly, why do you want to put parallel RC? I want to understand the thought process.
No.
So, okay. So why will the AC still be the same? Because
anyway the capacitor.
Okay. So let me remove the capacitor. So AC will still be the same? Loading will be worse or better? Why? What is the resistance looking into this? So let's say I call this RB. What will be the resistance looking in? Somebody from this side. It will be RB plus 1 over GM, right? Because ultimately this guy is 1 over GM and RB is in series with that. So this will be RB plus 1 over GM. Now RB is in your control. You are putting it. So you can make RB to be as high as you want. Right? Once you make RB to be as high as you want, then you can essentially say that as long as RB plus 1 over GM is much greater than RS, our loading is not a problem. Right? Make sense? So this is kind of one configuration of a common source amplifier where you make GM independent of threshold voltage variations. Okay. Any questions? Now, threshold voltage variation is not the only variation which affects the current. Mobility is also a strong function of temperature, right? So in case of mobility, if temperature varies, mobility will also change. And in a voltage biased transistor, right? When I say voltage biased, I mean you have biased with a constant voltage between gate to source. So in a voltage, so this is a voltage bias. This is current biased. So if mobility changes from mu0 to mu0 to mu0 plus delta mu, your GM expression is this. GM is so your GM changes by GM naught to GM naught plus delta mu n or delta mu times C ox times W by L over times overdrive, right? And this is, you can express this as delta mu by mu times mu. So this is GM times delta mu by mu, right? So this is GM naught plus. But in a current biased, in a current bias transistor, the corresponding equation that helps us helps in the maths is this. Because ID is constant, I don't have to bother about any other variable. So now if GM changes from GM not to plus delta GM, how much will if mobility changes by delta mu, how much will GM change? So I can do this, right? I can so this is equivalent to saying that delta GM will be right. So this is equal to how much? Calculate and tell me. Yeah. Give me an expression.
But C of WL ID upon GM.
What?
Delta means C of W by L ID divided by 2 root 2 into G.
Okay, concise form. Quickly.
C of W upon L ID upon GM.
No, that's not okay. I'll do it. So this becomes under root 2 C of WL ID, then 1 by 2 under root mu times delta mu. Right? So this becomes so if I want to express this in terms of GM, right, on the right hand side, so this becomes root 2 mu Cox W by L ID times, did I make a mistake? Oh, this is fine, right? No, this is fine, right? So I multiplied with under root mu and I'll divide by under root mu. So this becomes delta mu by 2 mu, right? So this becomes GM naught times delta mu by 2 mu. So in this case, the change in GM in the left-hand side is proportional to delta mu over mu. In the right-hand side, it is proportional to delta mu over 2 mu. Right. So in this case, as you can see that the change. I mean, even if you bias it with a constant current source, the effect of mobility is half. Right. The effect of change of mobility is half on GM with respect to a constant voltage bias. Right. So you gain in both fronts. Right. It's a change in mobility change in threshold voltage doesn't change GM at all. Change in mobility still changes it, but not by as much. Right. So this is a better way of biasing on both fronts. Okay. Okay. Fine. So we saw one way of biasing a transistor with a constant current source. However, that is not the only one. However, that is not the single way. There will be multiple ways because there are multiple ways of feeding current into a transistor. Right. So in a transistor, I have current. I mean, I can push a current into the drain of the transistor. I can pull current out of the source of a transistor. So essentially, there are two ways of feeding current, and there are also two ways of developing VGS. Right? I can either change the gate voltage, or I can change the source voltage. So essentially, there are two ways of feeding current and two ways of developing VGS. Do you agree? Till now, we have kept the source voltage constant to be grounded, but that it need not necessarily be the case. right? So I can either affect the gate voltage, I can either affect the source voltage in terms of feeding, in terms of affecting the voltages at the terminals, and in terms of pushing current in or out of a transistor, I can push current into the drain or pull current out of the source. So seems like there are 4 possible combinations, right? You pull current, push current into the drain, affect the gate, right? So I can say that I can push current into drain and then change gate voltage. This is one way of biasing. In principle, this is what we saw, right? The one that we saw was this, right? We were pushing current into the drain and feeding the drain voltage to the gate voltage. So similarly, I can push current into the drain and change the source voltage. In principle, it still can be possible, right? Similarly, I can pull current out of source and change the gate voltage, and I can pull current out of source and change the source voltage. These are the 4 in principle. In plain English, we can argue that since there are 2 ways of pushing in current and 2 ways of affecting voltages, there can be 4 possible combinations, and these are the 4 combinations. Out of this, one we have observed, right? So we like to observe the others also. So let's do the last one first. Next, rather. You'll understand why we are doing the last one next. So let's say, so last one is pulling current out of source and affecting the source voltage, right? So the statement is I have to use a current source connected to the source, right? So that's what we are trying to realize. So let's say this is the statement, right? We are connecting. This is all we know. This is given, right? So we have connected a constant current source to the source, and we would like to affect the source voltage. By this very definition, we are saying that we will not do anything to the gate, right? So when we say we won't do anything to the gate, which essentially means that we incrementally will not do anything to the gate, but the gate cannot be kept floating. So something needs to be connected, right? So some voltage source will be there. So let's assume we have some voltage source here, VG. Let's say VB. Okay. And we also, when we say we are not, there is nothing that is telling us to do. There is nothing here that is telling us about the drain, right? So let's keep the drain also to VDD. Okay. So now the question is, what we are trying to see is what should we do to the source to ensure that the transistor is automatically biased. Okay. So now again we'll do the same argument as we did in the previous class. So let's assume that there is a small capacitor here to help us understand the direction of the voltages. So now again, like previous class, we'll assume that we have connected it like this in the lab, and the transistor is giving us some current IDS. Okay. The transistor is giving us some current IDS, and the whole purpose is to ensure that the transistor is biased in saturation. We will be able to come up with a methodology so that the transistor is biased in saturation under this configuration, right? So that's the goal. So now we'll argue like we argued in the previous class. Let's assume that IDS is higher than I0. Right? We go and connect it like this in the lab. It's not necessary that IDS will be equal to I0. Right? So let's assume IDS is higher than I0. If IDS is higher than I0, what's going to happen to the source voltage? It will go up or go down? It will go up. Do you agree? The source voltage goes up. So fine, this capacitor, essentially if IDS is more than I0, the extra current will flow into this capacitor and this voltage will go up, right? So if IDS is more than I0, what is it telling us about M1? Is M1 stronger than necessary or weaker than necessary? Why weaker? Now IDS is higher than I naught, right? I want IDS to be equal to I naught. If IDS is higher than I naught, so the M1 is stronger than necessary, right? M1 is pushing more current than I naught. No, what will happen is the next thing. But let's say this is an observation. Let's say you observe that IDS is higher than I naught. Then what is the conclusion? The conclusion is M1 is stronger, right? And what is the observation? The observation is this source terminal is increasing. From that observation, you conclude that M1 is stronger. Is that fine? Fine. Okay. So if that is true, then what is the action? The action should be you have to make M1 weaker, right? So in order to make M1 weaker, I have to reduce VGA. That's the only thing I can do. I cannot change anything to the gate because connected with a constant voltage source. So I have to do something with the source. So what should I do to the source? Should increase or decrease? I have to increase source. But we see that is automatically happening, right? By simply connecting a current source to the source of the transistor, it seems like there is a negative feedback inbuilt, right? So if M1 is stronger than I naught, then the source voltage increases, and by that very action of source voltage increasing, it's trying to make the transistor weaker. If you think in the other way, if let's say IDS is lesser than I naught, then more current will be pulled out of that parasitic capacitance and the source voltage will go down, thereby trying to make the transistor stronger. And when will this fight between source voltage going up or going down stop? It is only when IDS will be exactly equal to I naught. Right? So which essentially means that you don't have to do anything. You connect your transistor like this, it will automatically bias to an appropriate value. VGS will get auto-adjusted to the value that is required for I naught. Right? So what will be the VGS? Your VGS under settled condition, right? Under settled condition will be equal to threshold voltage plus overdrive, where the overdrive is under root 2 I naught by mu n C ox W by L. Okay. So, any questions about this? So let's say now I want to bias this. This is all good in terms of symbols, but let's say I want to now go ahead and bias this. So let's say VDD is, let's say 3 volt. I told you I naught is 1 milliamp. Let's say this is 1 milliamp. And threshold voltage is 1 volt. Let's say threshold voltage is 1 volt. And mu n C ox, like whatever we have been taking till now, mu n C ox W by L is 2 milliamp per volt square and so on. So tell me I don't want any negative voltage in the circuit. So what is the minimum VB that I need to ensure that the transistor is in saturation? For why? How did you come up with that number? So let's say, by the way, I'm telling you mu n C ox, this guy is 2 milliamp per volt square. Okay. So calculate the VB that is required to ensure the transistor is in saturation, or rather calculate the VB that is required under the condition that there cannot be any negative voltage anywhere. Okay. 2 volt higher than Vs. That's good because VGS is equal to 2 volt, because under the condition that I gave you, VGS has to be 2 volt. So it has to be 2 volt higher than the source. So what is the source voltage? VB should be less than equal to 1 volt. Vs has to be less than equal to 1 volt. Why? What is so holy about 1 volt?
Otherwise, it will go into it will go into saturation region. So,
why do you say so? Okay, let me flip the question, right? Let me flip the question and ask and tell you that, let's say I in the lab I made VB is equal to 3 volt. Okay. So what will be the source voltage? 1 volt. Okay. So source voltage will be 1 volt. If I change it, if I now say that I change VB from 3 volt to 2.5 volt, what will be the source voltage? 0.5, right? So what are you observing? The source voltage is following the gate voltage. Right? Incrementally, the source voltage is following the gate voltage. Right? So this is often, that's why I call source follower. Right? Even though it should be called a gate follower. Right? So, but it's called a source follower. Right? So the source follows the gate. So so now, if I ask you the same question again, that I don't want any negative voltage in the circuit, what will be your thought process? Which means that if I, let's say I make VB equal to 0 volt and negative voltages are allowed, then can you comment on the source voltage? -2, right? Source voltage will be 2 volt lower than the gate voltage, right? And if I don't want any negative voltage, then what is the constraint? Then VB has to be greater than 2 volt. Right? So source voltage, which means that this voltage cannot be more, this voltage at least has to be greater than 0, which means VB has to be 2 volt plus the source, which means it has to be at least equal to 2 volt, right? In principle, these current sources are also made using transistors, which means that you would like to keep some drop across the transistor, across the current source, right? It will not be 0, it will be some positive drop. So in that case, you have to ensure that drop is fine, and on top of that, you have to apply the VGS. Okay, makes sense? I mean, now you are mature enough. Now in the course, we are mature enough to understand what this transistor, what this current source is. A transistor biased in saturation itself is a current source, right? So I can as well replace this current source using another transistor, right? So I can essentially say that this was the M1, this was VB, and this current source, whatever it was, I will replace this with another transistor. And by the way, when I replace it with another transistor, so the looking in impedance from the drain of the transistor is, if we neglect channel length modulation, is infinite, correct? And the looking in impedance and the impedance across the current source is also infinite, right? An ideal current source has infinite impedance, and the impedance of a transistor looking into the drain is also infinite, right? Ideally, so which means that I can replace this I0 with another transistor. Let me call this M2 or M0. Let's call it M0, right? And ensure that this guy is in saturation. If I ensure that this guy is in saturation, which means maybe I connect another battery, let's say VB0, and if I ensure that this is in saturation, then this current will be equal to something, will be I0 corresponding to M0, and then these two configurations are identical, right? Do you see that? Okay. So now the question is, how do I bias M0? How do I bias M0 to ensure that M0 is in saturation? Right. So we have seen multiple ways of biasing, right? So one option, I'll come back to what you said, diode connected, right? We'll see what happens if we diode connected this. But let's assume we have a battery, even though this having this VB naught like this is not particularly a good thing. So let's assume that VB naught has been generated from somewhere else, right? So just like here we did, we generated the VGS of M1 from another transistor and fed it back. Here I can generate the VGS of M0 from another transistor and feed it back here. I haven't just showed it here, right? So let's assume that VB0 is that. Okay. So if that is the case, then first thing I have to see is how do I ensure that M0 is in saturation? Okay. So let's see. So let's say M1 and M2 are identical. All the parameters of M1 and M1 and M0 are identical. So now tell me, if I want I0 of 1 milliamp, what should be VB0? Assuming M0 in saturation, I want I0 of equal to 1 milliamp, what should be VB0? This is what we want. Use this equation. 2 volts, right? So VV0 has to be 2 volt. So now this is the requirement of the VGS, but it's not guaranteed that M0 is in saturation. We have to ensure that the M0 is in saturation. So if M0 needs to be in saturation, what is the minimum voltage for this node Vx, let's say? It's not 2 volt, right? 2 volt definitely it's in saturation, but what is the minimum Vx, allowed Vx, minimum Vx for this guy to be in saturation, for M0 to be in saturation? 1 volt or higher, right? So this has to be greater than 1 volt, right? So if Vx is greater than 1 volt, what is the minimum voltage on VB? Because ultimately M1 and M0 are identical, and I know that this is 2 volt. Okay, so which means VB has to be greater than 3 volt. Okay, so if you ensure this, then this guy will get biased properly. Okay, so very often you will see that people will ask you, they'll give you some circuit and will ask you who is setting the current in this stack, right? The reason the question comes is when you have 2 transistors and I know that current equation is VGS minus VT whole square, then let's say I want to change current in this stack. I want to change current through M1. Can I change the current through M1 by changing the size of M1? Let's say I double the size of M1, right? If W by L was 10, I make it 20. Will the current in this stack change? Will the DC current through M1, M0 change? With this arrangement, it will not. Why not? Can you elaborate? He's saying no path for the current to go. Meaning there is current path. Right? I didn't understand.
Extra current or reduced current can go or come from.
Right. So his argument is if I increase the W by L of M1 and I assume that the current has increased, that extra current cannot go anywhere. Right. So any other comment from anyone? Is that argument valid?
Yes, so we can also understand by assuming the capacitors across the load and then check the voltages.
Okay, let's do that, right? So let's say
the same load,
right? So let's assume we have a small capacitor here, and you want to check the voltages. Let's check, right? So if you have if let's say you increase W by L of M1 suddenly, you doubled it, the current through M1 is trying to increase, right? So, but what about the current through M0? Right? So Vx will change, right? Vx will go up or down.
Vx will go up.
Vx will go up, right? So if you increase the W by L of M1, the Vx will go up. How much will it go up? This guy will tell you. Because I naught is being set by whom?
M1.
So who is setting the current in the stack? M naught. Because if I change W by L of M naught, will the current change? The current will definitely change, right? Because if I change W by L M naught, I mean, this is dB naught is constant and the current will proportionately increase, right? If I double it, the current will double, right? So this, whatever current I get from M naught is this I naught. This is the constant current. And now if I affect the size of M1, all that is going to happen is that the DGS of M1 will auto adjust to accommodate for that current, right? So that this current in this stack is being set by M0, right? Easy way to think is, if I change the size of a transistor, will the current change in that stack, right? So there will be the first order, right? So there will be one transistor for which it will change, and for the rest of the transistors it will not change. So whoever is responsible for change of current in the stack is setting the current in the stack. Okay. So now tell me what's going to happen if let's say I double the size of M0. Right? I double the size of M0. So you agree that the current I0 will change. Right? I0 current doubled. So what's going to happen? Now, because now current has doubled, but M1 size hasn't changed. Vx decreases, right? So VGS of M1 has to increase now. And it can increase because source is not stuck to any voltage. It's not like a common source amplifier where the source cannot change. Here the source can move, right? So the gate, now the source, the Vx, the source node will go down to accommodate for that extra current. Okay, make sense? Okay, fine. So this configuration is also often called a cascode configuration. And this transistor M1 is called the cascode transistor, which sits on top of M0. We will see later on what is the other implication of this. These type of configurations have far-reaching influences. Okay, so fine. So this is all right. Any questions? Okay, so if there are no questions, then let's explore this a bit more detail. So it seems like if this node Vx incrementally is following the gate voltage, right? That's what source follower was. So which means that if I apply a incremental input here, what can you, so let's say this is VSQ and this is VGQ. If I apply an incremental input to the gate, what do you expect the source voltage to be incrementally? If incrementally I increase, if I apply incremental input Vi to wherever I have shown, something will change in the source, right? So what will change? Or how much will it change by the source voltage? Is the question clear? So what I'm essentially asking is, this is VSQ plus Vs, right? So what is Vs? What is Vs over Vi? Can you calculate and tell me? So essentially this is, incrementally this is what? Incrementally, the gate is Vi. You have open circuit here, right? And this is shorted. So this is GM Vi minus Vs. This is Vs. So if I do a KCL at Vs, what do I get? GM Vi minus Vs equal to 0, which means which means Vs is equal to Vi. So this guy becomes equal to 1. Okay. So now this should not be any surprise, right? Given that we led up to this thing saying that this is a constant current source bias, the VGS is always constant. So if I change gate, source will also change accordingly, right? That's what we did here multiple times, right? So if we saw that if the gate voltage dropped by 0.5 millivolt, 0.5 volt, the source voltage also dropped by 0.5 volt. That is nothing but another way of saying that that incremental gain between the gate and the source is equal to 1. Okay, in the same direction also, not in the opposite direction, not like a common source amplifier where the signal swings are in the opposite directions between the gate and the drain. Here, between the gate and the source, signal swings in the same direction by the same amount. Okay, make sense? Okay, fine. So this seems to be a kind of, since this is a volt, it's following the voltage. This seems to be an interesting configuration, and let's say I want to understand that what happens. Okay, so okay, let's take a step back from there and then say that I want to turn this configuration into a common source amplifier. Right, that's what we have been doing. We want a gain. We want to turn this configuration into a common source amplifier. So in a common source amplifier, when there is an incremental gate voltage, we expect the source voltage. We expect there should be an incremental current through the transistor, right? In this case, do you have an incremental current through the transistor? If the gate changes, will there be an incremental current through the transistor? Essentially, what I'm saying is, can there be a delta I? Or what is delta I? Huh? Will be equal to 0, right? Because Vs is following gate voltage, VGS is 0, so delta I will be 0. Since delta I is 0, I mean, looks like this guy cannot be a common source amplifier, right? Because ultimately we want like GM times Vi current to flow through the transistor that I have to push into a resistor to get the gain, right? So that's a problem. So if I have to turn this guy into a common source amplifier, so firstly, I mean, this bias is necessary and this input is necessary. And in a common source amplifier, we also connect a load at the drain. And we take the output from here, right? This is the output. So in this case, if a configuration like this appears, what will be V0 over Vi? Can you calculate V0 over Vi and tell me? So since delta I equal to 0, so you'll not have any incremental gain, right? So incremental gain is 0, right? So V0 over Vi will be 0. And this definitely is not a common source amplifier. Okay. So now what is the root cause? The root cause is, as he pointed out, the source is open circuit. Right? Source is open circuit. So if this voltage changes, the source is following. Right? Not because it's open circuit, but because of this configuration. Right? So if gate changes, if the gate voltage increases, the transistor is trying to push in more current, but it cannot push in more current because it is biased with a constant current source. So the only way it can reconcile this problem is if it pushes the source along with the gate, right? If the source swings along with the gate, the difference between the gate and the source doesn't change, which means everything is satisfied. Okay. But in a common source amplifier, I don't want that. In a common source amplifier, I want the incremental current to be GM times gate voltage. right? I want the source to be incrementally shorted, right? But also in this configuration, I would like to use this constant current source bias, right? So what is the solution then? Right. So if I have to short it incrementally, we know, right? Now, if we have to shorten something, you just put a capacitor between that node and ground. So all the incremental current will now flow. If this capacitor is large enough, right? Let's say this C is infinity. Not this small parasitic capacitance, right? It is large enough. What is large enough? We know how to figure it out, right? We have done it multiple times. We have to find out the time constant associated with the capacitor and then make that time 1 over tau to be equal to, tau to be much, much larger than 1 over omega naught. And whatever you get from there, you get the constant on the capacitor. But the key thing here is, if you make this capacitor large enough at the frequencies where capacitor acts like a short circuit, then all the incremental current, right? So this current will be I naught plus delta I. All the delta I naught is flowing here, and delta I will flow here, right? And this, since delta I is flowing there, I can as well say that this is battery, right? So this, so you will have I naught times RL drop, which is the quiescent, plus delta I times RL drop, which is the incremental. And if you observe the voltage across the resistance, or incrementally the voltage across the transistor, you will get the gain to be rather voltage to be delta I times RL. This will be V naught. Okay, fine. Now the question is, obviously this is kind of obvious, but still let me ask you this question. So now this delta I is flowing into this C infinity. Why isn't it raising that voltage of source and shutting the transistor down? That's what we have been saying all along, right? So the way we bias this configuration is, we argued that there is a parasitic capacitance, current goes into the parasitic capacitance, shuts down the transistor, all those things, right? So why is it that not happening? Because clearly delta is flowing into C infinity. Right. If C infinity is large enough, right? It's like an infinite bucket of charges. A small delta I will not really cause any issue, right? So, and by the way, this delta I cannot be DC, because if it's DC, then how you can have an infinite capacitor, it don't really matter, right? The DC current, which means it is there for infinite time, so it will keep on ramping the voltage of the capacitor. If the capacitor value is very large, the rate of ramp will be slow, but eventually it will ramp up and shut down the transistor. But since this is an AC, right? It's a sinusoidal current, which means it's not getting enough time to ramp up or ramp down, right? Before the next cycle starts. So hence, C infinity acts like a short circuit. Since C infinity acts like a short circuit, you can say that the Vs is not able to keep up with the gate voltage change within that limited amount of time, right? So, okay, so what I am pictorially, it probably makes more sense. So let's say I have a capacitor. Okay, we have overshot. Okay, give me 1 minute. Let's say we have a capacitor. And I put a current through the capacitor, and the current is a sinusoid. This is I naught. Right? So what does the capacitor do? The capacitor integrates the current and develops the voltage. Okay. So essentially this guy will get integrated, right? If I start from t equal to 0, this guy will integrate and it will reach a maxima here and go to a minima here, and this will repeat. And this difference will be the amplitude of the voltage across the capacitor, right? So now if I have a high frequency signal of the same amplitude, high frequency current, so let's say I have a high frequency current of the same amplitude. So the capacitor will still integrate, but it will integrate till here and then drop and do this. So this amplitude, because it's not getting enough time to integrate, the voltage across the capacitor doesn't build up, right? So now if you keep on increasing the frequency, the voltage will not be able to build up at all, right? So hence, at infinite frequency, the capacitor acts as a short circuit because it doesn't get enough time to build up the voltage. The converse thing is that if the capacitor is large enough, then this effective build-up itself is small, right? So which means that the voltage across the capacitor doesn't change within that limited amount of time. That time is the important thing, and hence we call that capacitor is a frequency-dependent element because the voltage across the capacitor doesn't really get accrued if the frequency of the current that you are pushing in is very high. Okay, so that's essentially it. I mean, that's essentially the way of analyzing, coming up with basic topologies of circuits. We'll stop here and we'll meet after the mid-sem break. Okay.